Okay, back in my office so I can make a better video. So here is the boat, and it's like a box. Part of it's underwater and part of it's not. That's how boats work, right? Okay, so it's in its normal situation, the center mass is right there in the middle, and so it's all level and good. But if I move a box over here, then part of it's going to dip down, and the torque due to this mass from the center is going to be offset by the extra buoyancy force pushing up. And so that buoyancy force depends on the extra volume of water displaced, which I've shown here as this little rectangle. So this is the extra buoyancy force due to it tilting down. And there's actually a lack of buoyancy force over there, so you get a double. And that's a 5-degree angle. So we can calculate the buoyancy force as the density of water, which we represent with the Greek letter rho. That's just what we do. You could call it D if you want, but we usually like rho. It's cooler. G is the gravitational field, and V is the volume of the object displaced, which is just that thing right there. So it's a wedge. And so the volume of that wedge is going to be 1/2 base times height. So that's a 1/2. The base is L over 2. L is the length of the ship. And then the height, and then the width of the ship, which I just picked. So if I know this angle is 5 degrees, then the tangent of this right triangle is h over the base, which is L over 2, so I can solve for h. So I put that in here, and I get this expression. So it's density rho, g gravity, L squared, W tangent theta over 8. Now the torque depends on F, the distance from the pivot point, and the angle between the force and the pivot. So that's a different angle theta. And I'm just going to say that angle is 90 degrees so that it's pretty good. So I have F times R, and I'm going to say the location of this force is in the middle, so that's going to be L over 2. Yeah. Okay, so now the torque, which is the Greek letter tau, again, we think that's cool. That's pretty much what we use, tau. So Greek letters are tau and rho. Everything else is just normal letters. And then I just put in my force, and I put in my length, L over 2, and I get this expression right there. Now that's going to balance with the torque due to the extra mass moved over. So this mass m is moved over distance x. So then I have the torque due to that is mx times g, where mg is the weight. And then I just set that equal to the torque to the other side, and I solve for the mass right there, and then I put in x equals 30. I put 17. Let me change that. Let's see. Oh, I did do x equals 30. Okay. X equals 30. The length of the ship is 70. The width is 20. The angle is 5. That was from the script. The density of water is 1,000 kilograms per cubic meter. And that gives a mass of 1.9 times 10 to the 6 kilograms, which is super high. But, you know, if you don't say that mass, I think you'll be okay. But this is the important calculations. Here, I'll move so you can see the whole thing.